Welcome to Technically You, where machines meet meaning and tech meets talk. Today, we're jumping into the cab of a diesel truck, or at least into its brain, with a deep dive into SAE J1939, the protocol powering communication in heavy-duty vehicles.
That's right. SAE J1939 is a protocol that is always in use, and most aren't aware that it exists. So, if you've ever wondered how a vehicle's engine, transmission, brakes, and diagnostics all talk to each other, J1939 is the silent language that makes it all possible.
So, what exactly is SAE J1939? It's a set of communication standards used in heavy-duty vehicles. Think trucks, buses, tractors, construction equipment. It governs how electronic control units, or ECUs, talk over the CAN, or Controller Area Network bus.
Yep, and it was developed by the Society of Automotive Engineers, SAE. It defines things like message format, transport protocols, and parameter group numbers, PGNs, all to ensure seamless data exchange.
Fun fact, each message has a unique PGN, and that PGN tells the receiving module what kind of data it's getting. Engine speed, fuel rate, oil temperature, you name it. Now, let's talk about how does J1939 works.
J1939 is built on the CAN protocol, specifically ISO 11898. It operates at the data link and transport layers, giving it a structured way to send and receive complex messages between ECUs.
Right, and while CAN supports up to 8 bytes per frame, J1939 can handle much larger data packets using transport protocols like BAM, broadcast announce message, and RTS/CTS, request to send/clear to send.
Plus, it supports a data rate of 250 kbps or 500 kbps. Plenty fast for vehicle telemetry. According to the standard, the maximum speed of a CAN bus is 1 megabit per second.
The CAN communication protocol is a carrier-sense multiple access protocol with collision detection and arbitration on message priority, CSMA/CD plus AMP. CSMA means that each node on a bus must wait for a prescribed period of inactivity before attempting to send a message. CD plus AMP means that collisions are resolved through a bitwise arbitration based on a pre-programmed priority of each message in the identifier field of a message. The higher priority identifier always wins bus access. That is, the last logic high in the identifier keeps on transmitting because it is the highest priority. Since every node on a bus takes part in writing every bit as it is being written, an arbitrating node knows if it placed the logic high bit on the bus.
Now let's compare it to some other protocols. First up, CAN, ISO 11898. It's the base layer J1939 builds on, used widely in all kinds of vehicles for basic messaging.
Next, OBDI, or onboard diagnostics, used mostly in passenger cars. It's like the little sibling of J1939. It focuses on emissions and fault codes rather than full-blown vehicle management.
Then there's ISO 15765.4, which is used for diagnostics over CAN, sort of a bridge between OBD and J1939 in terms of purpose and implementation.
Each of these has its place, but J1939 is uniquely built for the big guys. Vehicles that need multiple modules working in sync, constantly.
So why use J1939? What are the benefits of it? Standardization. Every manufacturer knows what data to expect and how it's formatted. Scalability. Easy to add more ECUs without rewriting the playbook. Interoperability. Works across vendors and subsystems.
And don't forget, diagnostics. J1939 allows for real-time performance monitoring and error reporting, critical for reducing downtime in fleet vehicles. How is J1939 configured?
Oh, configuration is pretty straightforward, but requires precise attention. You need ECU IDs, source addresses, PGN mappings, and proper termination resistors on the CAN line.
Also, each device needs to know its priority. Message arbitration happens based on PGN and source address, so lower values equals higher priority.
Is there a limit to how many messages J1939 can handle?
Yes and no. Technically, there are 8,192 possible PGNs, but limits on bus load, bandwidth, and latency still matter. A cluttered CAN bus will slow you down.
Okay, here's a quick sidebar. J1939 is often confused with networking terms like VRF or VLAN, but it's really in its own lane. It's not virtual routing, it's embedded real-time control.
There are several layers to J1939 too. J1939-71 defines the application layer, data like engine RPM or fuel level. J1939-73 deals with diagnostics, trouble codes, and status indicators. Speaking of network layers, is J1939 susceptible to cybersecurity risk? Is it vulnerable to attacks?
Ooh, this is where things get spicy. J1939 wasn't designed with cybersecurity in mind. It's a trusted network, meaning there's no encryption or authentication by default.
So that means if an attacker gets access to the CAN bus through a telematics port or unsecured wireless gateway, they can spoof or inject malicious commands.
Unfortunately, yes, but there are ways to secure it.
Yes, J1939 can be secured by the following: firewalling ECUs, segment traffic using gateways, encryption tunnels, use secure backhauls for telematics, message whitelisting, only allow known good PGNs, secure bootloaders, ensure ECUs haven't been tampered with,
and regular patching of firmware, although not every ECU is easy to update. Where is J1939 being used?
J1939 is used in freight trucks, construction equipment, farm machinery, military transport vehicles, and marine vessels. What do you think the future holds for J1939?
With EVs, autonomous driving, and smarter telematics, J1939 might evolve or integrate with newer protocols like Ethernet-based AUTOSAR or TSN, time-sensitive networking.
But it'll still be around. It's robust, proven, and deeply embedded in vehicle infrastructure.
Okay, that is all we have for today's topic. So whether you're a fleet tech, a network engineer, or just a gearhead who loves to learn, SAE J1939 is an unsung hero of mobility.
And as we roll into the future of connected transportation, understanding this protocol is your pit stop to staying ahead and staying curious.